Narendra Babu sir,
Yes,
sir,
sir.
you okay.
Yes, yes.
Okay. Okay. Dear participants, good afternoon to all. So, welcome to the day 3 session 2 FDP. So, now I request Pravina madam to introduce the today's speaker.
Good afternoon to one and all. I feel it's my privilege to introduce today's resource person, Dr. Narendra Babu sir. Dr. Narendra Babu sir received his PhD and MTech degrees in the Electrical Engineering Department with Power and Energy System specialization from the National Institute of Technology, Meghalaya, Shillong in 2017 and 22 respectively. He received the BTech degree in Electrical and Electronics Engineering from Jawaharlal Nehru Technological University, Hyderabad, India. Presently, he is working as an assistant professor at School of Electrical and Electronics Engineering, VIT University from 1st September 2021 to till date. He has a research experience of 4 years as a senior research fellow or project associate with RECTPCL CSR funded project during 2017 to 21, Department of Electrical Engineering, NIT Meghalaya. He has an industry experience of 5 years as an assistant electrical engineer during 2010 to 2015. He has published more than 25 research journals, conferences, book chapter publications in IEEE transactions and journals, ITs and tailors and Francis journals with high impact factors. He received more than 350 Google Scholar citations with 11 H index and 11 I-10 index. He is the reviewer of several IEEE transactions, IET, Wiley, Taylor, and Francis and other SCI journals. He has worked as a technical program committee member at several international conferences organized in abroad and India. He is working as an associate editor in several journals. He has qualified and received the GATE 2015 and 2017 examination ranks in electrical engineering domain. He is a member of IEEE from 2021 onwards. His current research interests include renewable energy technologies, hybrid AC-DC microgrid, power quality, adaptive control, solar PV system, power management, and control of grid-tied inverters. I request Dr. Narendra Babu sir to continue the session. Thank you.
Thank you for the introduction. So, I'll share my screen right now. Is my screen is visible to you all? Please confirm anyone.
Sir, blank page is visible, sir.
Yeah.
Blank white page.
Now, is my PPT is visible to you all?
Yes, sir. Yes, sir.
Yeah, thank you. So, good afternoon, everyone. So, myself, Dr. Narendra Babu P. So, already, the madam already given my brief introduction. So, today I will start my presentation. So, my topic is power electronics converters control, and particularly in microgrid applications. So, what is the need of this control, and what are the applications of power electronics, and what is the future trends in power electronics? That things I will discuss in this presentation. So, directly I'm going to my presentation. Firstly, I will give a brief introduction about the microgrid system. So what is the problem? So next thing in microgrid system, so what are the problems and what is the research gap in this particular area that I will discuss in this presentation, and what we did in particular microgrid applications, how what are the topics what are the controls we have developed till now that we will discuss, and later on the future directions of this particular area that I will discuss. After that, some my key publications and conclusions and references. So coming to the introduction, so what is microgrid? So microgrid system is a small scale system, so everybody knows. And if you see the present scenario, if you see the latest what is the statistics of Indian statistics, if you see the foreign statistics also, the microgrid systems are increased day by day, and also the control of these particular area have been researched in recent years, and it is a trending research area. If you see the next 5 years, the power alternate converter based systems comes as a very huge and very important research area in the further years. So it particularly, what is microgrid? It is a small scale system. It is, and it also grid connected, and as well as the islanded mode. If it is a grid connected mode, if it is a grid connected mode, all the local loads which are connected, which is nearby to the local system. Suppose if the grid is isolated from the microgrid system, then the microgrid system can give the power to the local loads continuously. So that is the reason the microgrid systems are very important in the present scenario, and it enables to deliver the power to the local loads, and it comprises various several power generating sources, which makes the micro systems is highly flexible and more efficient. And it's comprised of, already I have given, because microgrid systems comprises of several renewable energy sources like solar system, PV, battery, and supercapacitors, etc. So it is connected both grid connected mode as well as islanded mode. So that is the beauty of the microgrid system. And if excess power is available in the microgrid system, it can be sold to the utility grid, or it can be used for the local loads. And the size of the microgrids can range from a small scale to a large scale also results. So what are the problems in microgrid system? If you see the microgrid system, we have several types of problems. Mainly, we have to control the voltage, frequency, and power quality. And also, we have several problems such as grid synchronization, high impedance faults, protection, and stability. So in microgrid system, particularly, we have to mainly control three main parameters. One is voltage, frequency, and power quality. These are the main important parameters. These parameters we have to control in microgrid system. Otherwise, if you not control these parameters, so we can't connect the renewable energy system or microgrid system to the utility grid. And also we have to take care of these particular three parameters, that voltage, frequency, and power quality. We have to maintain these parameters within the IEEE standards or IET standards or any international standards. So based on the IEEE 519, IEEE 1549 standards limits, we have to interconnect standards. We have to maintain these standards within the ranges. So this is the basic block diagram of the microgrid system. Here you can see here the photovoltaic system, wind generation, and battery banks is connected from the renewable side, and these all are connected to the DC bus by using a boost converter. So why the boost converters is required? See, if you see the temperature and irradiation levels of the PV cells is not a constant. Everybody knows, so the temperature is not a constant. Irradiation will be changed based on the atmosphere. So these parameters are not constant. If you see the wind energy also, the wind speed, the wind speeds and velocity is also not fixed. It will be variable. So that is the reason the voltage of this particular renewable energy source is not constant. But if you want to maintain the DC bus voltage at a constant value, so we have to boost that voltage from different ranges to a constant voltage. So that is the reason we have to install a boost converter. So after the boost converter, So in the at the DC bus terminals, the DC bus voltage will be maintained constant. So if you are not maintain constant DC bus voltage, we can't send the maximum power from the utility from the renewable energy sources to the local loads or utility grid with unity power factor. So that is the reason the first thing in the microgrid system is one important control is DC bus voltage control. And here you can see the battery bank. So why we are using the battery bank means, see, suppose if the power is normal, if the power is available from the PV photovoltaic system, then directly the power will can be delivered to the DC bus, and after that by using voltage source converter we can send that power to the local loads. So if the deficiency of the power from the renewable energy sources, if when the deficiency of the power from the renewable energy sources, at that time the battery bank will give the power supply to the local loads. So that is the reason by battery backup purpose, power backup purpose, we are using a battery bank here. So for here particularly in DC microgrid system, one thing we have to control two areas. One is a DC bus, and second one is voltage source converter. So in the because several loads are connected in DC applications, so that is the reason we have to maintain the DC bus voltage with a constant. Otherwise, we can't send the maximum power to the utility grid. So another control. What is the another important control? The voltage source converter control. So this is very important. If you see the conventional control schemes, the performance, if you see the performance wise, if you see the research of previous research, in the past research, several researchers and several scholars have published so many papers on this particular area. But I have gone through the every from 1965 to 2021, between this duration, we have researched several papers, and the performance, if you see the performance wise, the conventional control scheme performance is not accepted during grid dynamic or grid transient conditions. So that is the reason we have to control, we have to develop an adaptive control scheme. So why the adaptive control scheme is required? So if you see the DC bus, if you see the DC bus, the conventionally the PI control scheme has been used from the long time. But if you see the load variation, if you see the load variation time, the grid load or grid voltage variation time, what will happen to the DC bus? The DC bus may increase or decrease. But we have to control the DC bus. If using the conventional control scheme, so we have to set that P and I values manually. So if the load is increased, then automatically the DC bus voltage will be increased or decreased. So we have to control that DC bus voltage adaptively. So how we will how to control that adaptively, that we will discuss in further slides. And another thing, in this grid source inverter also, in the grid source inverter control, we have several control strategies. But if you see the grid dynamic conditions and load dynamic condition, the performance, the conventional controls are failed completely. They have failed in the normal, in the steady state conditions, everything is okay, fine, all controls are same performing. But if you see the dynamic state, our control should be gives the best performance compared to the others. So in the microgrid system, the main motive is to have to control two areas. One is DC bus and another one is AC bus. Another one is grid source converter. So these things I will discuss in this particular presentation. So what is the research gap that already I have explained in the previous slide? So what is the research gap in this particular area? Well, the first thing is DC bus inverter. Second one is AC bus control, what is that? Voltage source inverter control. So these two areas are the research gap in this microgrid system area. So if you see the literature survey from 1999, if you see the IEEE transaction industrial, they have given a brief review about what are the harmonic sources and what type of filtering techniques are available. Everything they have given a brief review they have given. And if you see in 2003, so the authors have proposed passive filters. So if you see the conventional one starting, if you see the 2003 and before that, only passive filters are used to particularly for power quality improvement or harmonics reduction and everything. But the drawbacks of passive filters are they are huge in size, and also by using these passive filters, we can remove only a particular selective harmonics. We can select only, we can remove either one or two or three. For every individual harmonic, we have to design a separate passive filter. So that is the reason that this is one of the major drawback in passive filter. In the year 2014, in the active power filters are introduced. So to overcome these drawbacks, what are the drawbacks? Because in the passive filters, the size is huge, and also what is the another main drawback? We can remove only particular selective harmonics. So that is the major drawback in the passive filters. So to overcome these drawbacks, in 2014, several others have published several papers on active power filters. So active power filters are mainly classified into three types. One is shunt, series, and compound. If you're using a shunt active power filter, we can remove the current harmonics. If you are using a series active power filter, so we can remove voltage harmonic. If you are using a hybrid active power filter, we can remove both the series and both the current and voltage harmonics. And in this particular paper, they have given the design parameters of how to design a shunt, series, and a hybrid active power filters. So if you see the next 4 to 5 references, the researchers have been published several control strategy. That is the conventional control strategy. The first basic control strategy is instantive reactive power theory, which is also called as IRP theory, well known, and another one synchronous frame and phase compensation theory. So these three theories are basic theories. So if you see the performance phase, the steady state, if the grid is steady state, then the performance is very good, the performance acceptable. And the THD analysis, if you see the THD of the grid currents and voltages are within the limits of the IEEE 519. Based on the IEEE 519 standards limits, we have to control the grid currents THD within the 5%. So by using these theories, the others has reduced from 28 to 30% based on the what type of loads they have used, what type of switches they have used. Based on that, they have reduced from 30 or 25 to less than 5. I think I think it is around 4%, 3 to 4%. So the performance, if you see the steady state performance, it's the conventional control give the best performance. So, but because the grid is not stable, the voltage may be high or low based on the loads which you are connected. What loads you are connected, suddenly the loads will be disconnected, suddenly the load will be added to the grid. So based on this high switching characteristics loads, what will happen? The current or voltage harmonics will be high. So at the situation, at that conditions, that conditions is called as transient conditions or dynamic condition. These conditions, these control schemes, if you are applying these conditions, the performance is not acceptable and some controls has been failed. So that is the reason we have to implement another control schemes for particularly in dynamic condition. So in 2014, several others has been published, notch filter based techniques, and 2014 another neural network techniques based control schemes they have developed. And if you see this performance also, if you see the notch filter, it has a lower harmonic filtering capability, and particularly these type of notch filter and neural network technique are failed in DC offset rejection capability. And also if you see the ANN based technique, everybody's know the ANN techniques. It is very difficult to finding the proper learning. That is one of the major drawback in the neural network based technique, and also it is not applicable for DC offset rejection. So next coming to the 2016 and several after because previous ANN based notch filters are not applicable for DC offset. Here also several papers are published, several adaptive control. These are for least mean fourth Kalman based filter, ILST, variable step size, least mean square, and echo state network. These controls are for adaptive control schemes. But if you see these control drawbacks, we have found several drawbacks on the particular recent published work. Because if you see the LMF, if the steady state response is not adequate, and also the complexity wise, because we have to check the complexity of the controller, because we have to check the execution, how much time is taking when you are implementing the control scheme in the microgrid system. That is very important thing. We have to implement low complexity control schemes. So if one of the major topic is least mean square, this common weights filter, more complexity and more computational burden. And if you see some other topics also, these control schemes are not applicable. The dynamic, if you see some condition, the dynamic performance is fine, okay. But if you see some more condition like DC upset, so if you see the DC upset, we have to maintain DC upset at 0. If you are not maintaining DC upset more than 0, what will happen? Automatically, what are applications? So end users, those who are connected the PCs or laptop and other sensitive equipment, they will be failed, or sometimes they will be damaged. So that also we have to taking care in the particular research area. So that these control schemes are failed, particularly in DC offset rejection. So in 2018 onwards, several researchers are particularly they have considered all these steady state things and dynamic conditions, and also one of the most important what is that most important thing in DC offset rejections. So this is also they have to take care in 2018. In 2008, they have developed the second order based general, actually these generalized integrated based control they have developed. So particularly this SOGA based controls is very simple design, easy, less complexity, less computation burden, and also it is very much useful for DC offset rejection. So what what is the research gap in this particular area? So we have to maintain the power quality, voltage, and frequency. These things are the main parameter that we have to control within the standards, and also the control should be work in the normal condition as well as dynamic conditions as well as DC offset rejections. So these things we have included our research area. So what research I did in my in the previous last 4 years, that we will discuss one by one. So in the work one, so we have developed a normalized least mean square grid connected inverter control, and also the fuzzy logic based PID control for DC offset. So why we are using fuzzy logic? So how it is adaptive? How it is adaptive? Because the conversion already I have explained in the last introduction slide. Because the conventional PI control scheme performance is not acceptable during grid and load dynamic conditions. So how to control these things? That is the reason we have developed adaptive fuzzy logic PID. Why you are using fuzzy logic? So based on the error change in the fuzzy logic controller will calculate Kp, Ki, Kd values adaptively based on the DC bus voltage variation. So if the voltage is increased at the DC bus side, the fuzzy logic PID controller can calculated their Kp, Kd value based on the grid voltage. If it's grid voltage varying at the time, the fuzzy logic will calculate their Kp, Kd adaptively. So that is the reason this control scheme is called as an adaptive control scheme. Here the normalized least mean square control scheme we have developed for the grid side inverter. So this is the here particularly we have considered three-phase AC supply, and we have considered uncontrolled bridge rectifier circuit. And here and this two we have developed these two control strategy. One is fuzzy based PID, that is for DC voltage, and second one is normalized least mean square for the grid side inverter. And this paper we have published in Energy Sources Part A. And these are the complete control structure of the proposed adaptive control scheme. See, you can see these type of controls. These type of controls is working based on the fundamental weight components from the grid load currents and grid voltages. So first thing in the first step, here we have given load currents, because based on the load, the grid currents and grid voltage contains harmonics. So that is the reason we have given load currents are input to the controller, So based on in the load currents, we have two types of components. One is fundamental component, another one is harmonic component. Particularly this type of controllers, the working principle is it extracts the fundamental components from the load currents and remaining harmonic components give to the controller. So based on that controller, based on that extraction, the controller can calculate the pulse width modulation for the power electronics converters like VSA grid connected inverter, and see if you see the fuzzy logic design also here we can given the VDC, that is the actual DC voltage. The VDC star is the reference DC voltage. So we have to maintain. So how much? So maybe some anyone can ask any question on this particular area. Why we have to maintain the DC volts? So how much we have to maintain? Suppose if you are maintaining a 415 voltage at the grid side, if you are maintaining if you are giving a grid voltage 415, so how much we have to maintain at the DC at the DC bus? Anyone anyone from the participant? Anyone have any idea about this? Why we are maintaining? Why how much voltage we are maintaining from the DC bus? Am I audible to all?
Yes, sir.
Yeah. So how much we have to maintain? That is actually very important thing. So if you are maintaining a 450 volt DC, 450 volt AC supply from the grid side, so how much voltage, how much DC voltage we have to maintain from the we have maintained from at the DC bus terminals? Approximately. Okay, fine. So because we are using in the DC to AC, we are using already our grid connected inverter. So inverter having a switches, maybe IGBT switches, MOSFET, based on the application. So if you are using a switches, automatically switches have so many losses. So if you are giving 415 volt to the at the DC bus, if you are maintaining 415 volt at the AC bus, so based on this, due to the switching losses, what will happen? The output of the inverter will be output of the inverter voltage will be low. So that is the reason we have to maintain the more than one. We have to maintain more than grid voltage at the DC bus. So how much we have to maintain? So in roughly we have to maintain, if you are maintaining 415 volt DC AC grid voltage, so we have to maintain 1.5 times of the AC bus voltage. Suppose AC bus voltage 415, so 1.5 times of the 415 voltage approximately 700, 650 to 700 voltage we have to maintain at the DC bus. Otherwise we can't send the maximum power to the from the renewable energy source to utility grid, because we have a several losses because of the high switching devices connected in between DC and AC sources. So that is the reason we have to maintain the more than DC, more than grid voltage. That is approximately 1.5 times of the grid voltage. So that is the reason we have to maintain the more than 1.5 times of the that is actually our reference voltage. So if you are maintaining a 415 volt AC bus, so you have to maintain exactly 650 to 700 volts at the DC. So VDC star is the reference DC voltage, VDC is the actual voltage. Maybe the actual voltage may be vary, but we have to maintain our DC bus is reference voltage. Maybe it's 650 to 700 volts. So that error we have given to the fuzzy logic. So based on the error, how much error is there? So based on the error, the fuzzy logic desire can calculate the Kp, Ki, Kd values based on the actual voltage of the actual error of the DC bus. So like that, the fuzzy logic base will work in the system. So here we have developed this particular control and simulation based platform as well as experimental platform. So these are the parameters we have considered: three-phase supply, voltage I have considered through 230 volt, and frequency, and the impedance of the grid is 2.5 ohms. The inductor, coupling inductor of the microgrid is 2.6 milli, and capacitors for storage purpose the 2200 microfarad And here I am the voltage of the grid is 230 volt. So based on the DC voltage link formula, we have find out the actual what is the exact reference voltage of the DC is 375. So we have calculated based on the formula that 1.5 5 times of 230 volt is approximately 375 volt. That is our DC link bus voltage. Here we have considered particularly in PV system in this particular paper. So the maximum power 1.5 kilowatt, radius 1000 fixed, that is the fixed, open circuit 200, short circuit of 7.5 ampere, and maximum we got 190 volt, maximum PV current 7.3 ampere after the boost converter. And series number of series cells are 6, number of parallel cells are 1. Why particularly we have considered these rating? Because in our in my university we have developed a prototype experimental setup by using these parameters. So that is the reason we have considered these parameters for the PV system. And particularly in this MATLAB platform, we have simulated several dynamic load as well as grid condition, and we have taken grid voltages and currents, load voltage, load currents, and proposed controller calculated currents and compensating currents, DC link voltage, and different control characters also we have calculated in each and every condition. See, you can see here the first we have given the steady state condition in 0 to 0.1 second. 0, if you see the 0 to 0.1 second, that is steady state condition. So we have not given any external loads, external things in this particular area. Only 0 to 0.1 second, the system is running under steady state condition. So after that, 0.1 to 0.3, 0.1 to 0.3, we have considered the voltage swell condition. 0.1 to 0.3 seconds, we have considered voltage swell. So we have given 10% actually based on the IEEE standards. So the grid voltage may vary up to 10%. So 10% is acceptable. It's more than 10%. It's not acceptable. So that is 10%. We have increased the magnitude of the grid voltage for creating the voltage cell. And similarly, after 0.3 to 0.5 seconds, we have reduced the magnitude of the actual voltage to less than 10%. So that condition is called as the voltage sag, voltage swell, voltage sag, and steady state condition. So if you see the second one, this is source currents. Source current, if it is 0 to 0.1 condition, here particularly we have not applied our control scheme. If you see this duration 0 to 0.2 seconds, we have not applied any control scheme. So without control scheme, if you see the voltages is maintained constant, there is no problem in the voltage. So if you see the current due to the load, what load you have considered, what load you have used. So here I have used a uncontrolled diode bridge rectifier circuit. So due to that reason, the source current contains so many harmonics. If you see this three-phase waveform, is this visible to you? It is not sinusoidal, right? It is not sinusoidal because we have not applied any control. So that is the reason the load current is equal to the source current. There is no change in the source current. So if you are not applying any control scheme, if you are connected these currents to the utility grid or loads, so what will happen? Automatically, our appliances, the end users appliances will be destroyed. So we have to control these parameters. So that is the reason after 0.2 seconds, we have applied our control scheme. We have applied our control scheme. Then you can see here. So before that, the source current contains so many harmonics. Source current contains so many harmonics. And if you see after applying the controller, the all three phases currents will be sinusoidal. After applying this voltage swell condition also, after applying the control scheme, the currents are maintained sinusoidal. Then voltage sag condition also, after applying the controller, the voltage, the current is maintained sinusoidal, and the THD content of the this particular microgrid system are less than 5%. The third figure is load currents, and this current is the error currents. So what are the error currents? That actual currents in the controller, we have calculated some error currents. So based on the error currents, the controller can calculate the compensating currents. So these are the error currents and these are the compensating currents. So what is the compensating currents here? So compensating current is nothing but if your system having a harmonics, if your system having a harmonics, so several type of harmonics. So by using this controller, the controller can develop anti-harmonic current which are opposite of the harmonics, exactly 180-degree opposite of the harmonics. So after injecting this compensating current, the actual harmonic currents plus this current will be cancel out each other. Then your currents are maintained as sinusoidal. So this thing you can see the voltage, DC bus voltage also in the swell condition. Before that we have not applied any DC, so that is the reason 0. And after that 0.2 to 0.3 second, the voltage swell condition. So the voltage is maintained at 370 to 400 volt approximately. So because we have increased the voltage, actual voltage is 375. But if you see here, actual voltage is 370, but we are increased the voltage for the checking the dynamic performance of the controller. So the voltage is increased. So here the DC voltage also increased. So this for if you see the conventional one that is always fixed because we have given a constant kpk values to this particular conventional controller. So that is the reason the conventional control performance is not acceptable. So this is because we have proposed a fuzzy logic based control. The fuzzy logic is here we have used to calculate the kpk KD value based on this grid voltage. So grid voltage increased, so this voltage also increased. So here you can see suddenly 0.3 second I have reduced the voltage levels from normal voltage to the normal voltage to the low magnitude because of the checking the voltage sag condition also. See here they have maintained less than 375. Here less than 375 because the voltage magnitude is less than 375. That is the reason. So that controller is calculated based on the grid voltage variation. So if you see the THD analysis, so we have considered 4 steady state, voltage sag, voltage swell, and on one dynamic load condition also. So for steady state condition, we got 3.32%. Without controller, we got approximately 28%. So after applying the control scheme, the THD analysis has been reduced from 28% to 3.32 and at steady state condition. If you see the second one, this is the voltage swell from 28 to 3.68, and next the C figure sag condition 2.86, and the fourth figure a dynamic load condition. In the dynamic load condition also we have reduced from 28 to 3.0%. So all conditions we got less than 5%, and all THD are within the IEEE 519 standard limits. And this is our experimental setup. We have developed a prototype experimental setup in our university. So this is 1.5 kilowatt. This is actually a mistake, not 1.6 kilowatt. So 1.5 kilowatt PVRA. And here we have used a DSpace 120 evaluation kit. And this is the power analyzer. And we have considered a nonlinear load. This is the 3-phase resistive load we have considered. This is 3-phase resistive load for creating the dynamic load conditions, and this one is the linear load, and this is the auto transformer for creating the voltage sag and voltage swell conditions. And this is the current sensor circuit and voltage sensor circuit. So directly we are using a DSpace MATLAB supported DSpace platform. Directly we have connected that platform to a microgrid system, and by using this complete setup, we have developed PWM signals for the grid interface connector. After developing these 6 PWM pulses, directly that pulses we have given to the real-time 3-phase inverter. So these results we got in the on this particular platform. So if you see this first case, first one without compensation also, if you see the without compensation, the currents, this is the current, first one is current, second one voltage, third one load current, and finally load voltage. So if you see before compensation, the contains so many harmonics. After applying the controller, the current the harmonics are low after applying the control structure. So this is the one condition, and here sag and swell condition. Voltage swell condition also we have verified. See here, voltage we have at this in this particular area, voltage is constant. So here we have increased the voltage. We have this is voltage swell and voltage sag. Voltage swell and voltage sag condition. Swell condition, the current is maintained, will contain less because we have to maintain the power balance at the grid side. So that is the reason the magnitude of the current is low, because the current is high. Here the current voltage is low, current is high because of the power balance from the grid to load. So that is the reason here the magnitudes are changing. So these are the control characteristics of the proposed systems. And after that, we have compared these control schemes with the conventional control scheme. The first thing, conventional based control schemes are IRP theory. So instant reactive power theory, we have compared. So SRF, LMF, VSS, LMS, ILST, and eco-state network. And these are the conventional IRP, SRF are the conventional theory, LMF, VSS, ILST, ESM are the recently developed control schemes. So we have compared conventional as well as a recently published work and different features. What type of the controller, and what is the complexity of the controller, and what is the THD current, THD content of the current, and what is the dynamic performance, what is the performance, how the control is performing at the dynamic condition, and what about the power factor, and how these controllers are tracking their amplitude, and what are the oscillations. So how many oscillations in the current source, current side, how many oscillations at the grid side, grid characteristics. Everything we have compared, and different features with different control schemes. If you see all the features, our proposed control schemes are gives the best performance. If you see the THD content also, IRP got 3.12, this is 3.65, 3.45, 2.9. Our control gives the 2.86%. So we got the less in THD content, and the dynamic performance also. In the dynamic condition, IRP is very poor. Dynamic performance is not acceptable. And LMF, these bases are okay, good. The performance, this LMF is medium. The remaining all three are good. But this proposed is give the better performance. And power factor corrections also, these the conversions are not acceptable, and these power factor in this particular recent published work have some medium performance for the power factor correction, but the proposed gives the good performance. Amplitude, how amplitude tracking capability, so conventions are not applicable for this amplitude tracking feature. So remaining all are applicable, but they have not given a good performance, and they have given the good performance, and this one also is the good performance. So oscillations, remaining conventional one, oscillations are very high, and our proposed oscillations are very low. So this is the detailed comparative analysis with conventional and adaptive control scheme. So in the next work two, in the work one, we have developed adaptive controls at the DC bus terminal. At the same time, another control we have developed for normalized least mean square based control for the grid connected inverter. But in this particular work also, we have find several drawbacks. What is that? Already I explained the first starting slide. What are the main important drawback in the microgrid is DC upset. What are the main important? DC upset. So what is the DC upset here? So what is the DC upset? The mean amplitude of the grid currents is equal to 0, then your DC upset is equal to 0. It may be DC if the DC upset is high. If the DC upset is high, that means what? Your three phases are not maintained the constant magnitudes. The magnitudes are different magnitudes, so that what will happen? The system, those appliances or connected that will be destroyed. So we have to maintain all three phases at same magnitude. So if the magnitude is not maintained, so your DC upset is not 0. So we have to control the DC upset. So if you see the previous one, if you see the LMS based control scheme, that control scheme is not applicable for DC upset. But already explained in the literature survey, and what are the important what is that research gap in this particular area, DC offset rejection. So here in this particular work too, we have considered a DC offset rejection. The control should be cancel out the DC offset and current and voltage harmonic elimination. See, if you see the previous one, only we have considered only current harmonic elimination, right? And also that control is not applicable for DC offset. So here, but to overcome these two drawbacks in this particular paper, we have considered these two parameters, DC offset rejection and current and voltage, both. Because if you see the literature, only hybrid active power filter can eliminate current and voltage harmonics as per the literature. But here only we have used a shunt compensator. We have used shunt compensator. By using this shunt compensator, we have already removed current and voltage harmonics. So what is the advantage here? If you are using hybrid, so you have to use series and shunt. So for the current and voltage harmonics. So if you are using here, we have used only shunt compensator. Moreover, we have eliminated current and voltage harmonics. That is, so what is that main advantage? So the complexity of the system is low. You want to eliminate this current and voltage, you have to implement, you have to design a hybrid active power filter. But here we have, by using this shunt active power filter and this proposed control scheme, we have removed current and voltage harmonics and DC offset rejection. So what type of control we have developed? That is fuzzy logic based PID. That is for DC voltage. That is, this is same one in the previous work. And here, to overcome this DC offset rejection and current and voltage, we have developed a MCCF, the multiple complex coefficient filter based controller. That is designed for voltage harmonic elimination, and the MSOGI, the multiple second order generalized integration based frequency lock loop controller we have developed for the grid side inverter. So by using the combination, this is the combined, this is a hybrid control scheme we have developed for the microgrid system for power quality improvement, DC offset rejection, grid synchronization, everything. So we have designed this control scheme, and this paper has been accepted in IEEE System Journal. So this is the overall control structure. Here we have designed the MCCF based controller. The MCCF is used for the voltage harmonic. This is also used to extract the fundamental components from the grid voltages. Grid voltage only. This is for grid voltages. We have given VS ABC source volt grid voltage. We have given to the ABC to alpha beta transformation. Because why we are using ABC to alpha beta? Because to reduce the control complexity. So if you are giving directly three-phase voltage to the controller, what will happen? So each phase we have to connect a different frequency, different things, different parameters we have to use. So if you are converting a three-phase to two-phase, then the control complexity is low. So that is the reason we used the ABC to alpha beta. After that, we have used a reference frequency. So after that, the controller, we are giving the fundamental components. One is alpha component and beta component. Finally, we have given alpha beta 2. So inverse Clark transformation we have used for this one area. So alpha beta 2, inverse alpha beta 2 ABC. Then finally, we got the fundamental components of the grid voltages. So if you are, this is the conventional, this is the fuzzy logic period that I already explained in the previous slide. And this is MSOGI. So what in the literature survey, that one of the researchers has been published only one paper on SOGA paper. So if you are using one SOGA, the control performance is okay, acceptable. So if you are using more, SOGA, so if more SOGA that is connected in parallel, so what will happen? So that we will research. So we have connected 4 SOGA in parallel. Then the output of the controller is the best performance compared to the single SOG. So this is the overall complete control structure of the MSOGA QSCFLL. And here we have considered a P photovoltaic system peak power and compensation, because during the load and particularly load dynamic conditions, the grid, what will happen in the system, the DC bus voltage will be changed. This is the main drawback. So that is the reason we have used PV feed forward component. That also we have included in the particular control system. By using this parameter, what will happen? The performance is more accurate compared to the previous one. After adding this feedward component, the performance is more accurate compared to the previous one. That is the reason we have included the PV feedward component. So here also we have tested simulation based tests under several test conditions, steady state, here load remove conditions and dynamic load. So if this is the steady state condition, this the first one is voltages, the second figure is currents and load currents. So alpha beta components of the MCCF. So then finally the output voltages of the grid side. This is the grid side. This is the control characteristics of the MCCF. For the, to checking this performance MCCF, to checking the MCCF control performance, we have manually injected the harmonics at the grid side. So how this MCCF is working. So that is the reason manually we have injected some harmonics at the grid side. So if you see the alpha beta, so the controller has been removed all the harmonics at the grid side and give the pure sinusoidal voltage at the grid side after applying the MCCF. Then the error currents of the control. This is the MSOGA control characteristics. The quadrature, the already I have given statement of this particular this type of control. SOGA based controllers are working based on the fundamental extraction from the load currents and some internal parameters. So here the output of the control is two types of components will get at the output of the controller. One is a quadrature based control, quadrature based characteristics and in phase component. So this is the quadrature, the internal characters of the control quadrature component, and this is the in phase component. So both components we have extracted. So this one is unit vector template voltage, and this is the net current, I net current of the voltage, and this is the reference current. Finally, the reference currents of the proposed control we have calculated. And if you see the DC bus voltage, and here we have extracted the frequency also. We have extracted the frequency. If you see the frequency, the entire operation, the frequency is around 3.14. Around 3.14, that is actually acceptable range in the microgrid system. In the test case 1, you can see the THD. Another thing is THD. The THD is, see, in the first test case 1 steady state, we got 2.78 from 28 to 2.78. In test case 2, the load remove condition, we have removed one phase. We have removed one phase of the load because we have to check the controller dynamic performance. We have to check the controller dynamic performance. We have manually removed one phase from the three phase load. One phase we have removed. So at that time, so the THD NS we got very good performance, particularly in this load removed condition. From 28% to we got 0.26%. So in the particular load remove condition, we got very good THD content. So in test case 3, we got 3.02. So dynamic load suddenly, see if you can see 0.15 second, we have increased the load. Suddenly we have increased the load. So at this situation, how my control is working, how the performance of the control, that also we have verified. So in this particular condition also, the controller gives the best performance, and we got 3.302%. And this is the experimental photosite setup. The first work we have used a D-space based experimental platform. Here in this particular work, we have developed a FPGA based photosite setup in our university. Here a 1.5 kilowatt PV panel we have installed in our university, and this is we have taken the three-phase grid supply from this three-phase source, and this is the resistive loads, power analyzer for taking the result. This is three-phase resistive load, rectifier circuit, and sensor circuit, and this is grid impedance, and this is auto transformer for increasing the decreasing loads, and this is the coupling inductor. This is complete. This is actually the main important parameter in the microgrid system is the voltage source inverter. So this is the central computer. Firstly, we have developed our system, our simulation system in a Xilinx system generator. That Xilinx system generator software is supported for the FPGA based system. Firstly, what we have developed, first the simulation based system we have developed into FPGA supported Xilinx system generator system. So after that, the Xilinx system generator will give the code for the FPGA interfaces, that VHDL code, very log HDL code. So that code is dumped in this FPGA interface kit by using the central computer. So that code directly, the VHDL code we have dumped into the FPGA interface kit. So after that, this FPGA interface kit will give the PWM pulses. So that pulses we are directly given to the voltage source inverter. Then this voltage source inverter will develop the anti-harmonic current. That currents will be useful for the harmonic elimination and power quality improvement in the grid connected system. And we have taken all the results by using this power analyzer. And three-phase auto transformer for voltage increase or decreasing purpose, and this particular resistive load for sudden load increase or decrease. So this is the rectifier circuit which is acting as a non-linear load in the microgrid system. So these results we got in this particular FPGA platform. So first case is instrument result under steady state condition. See, in the first phase, source current, and the first figure is source current, source voltage, source current. If you see the control, if you see the one, the DC offset is completely zero. Here you can see the DC offset is completely zero. The voltage magnitude also maintaining zero offset, and also harmonics are very less in this steady state condition. And these are the load currents, and this is the internal characters of the alpha beta component of the MCCF. MCCF internal characters also we have calculated in the real time. And this one fundamental components of the voltage, that is MCCF controllers output. And these are the control characteristics, reference voltage A, B, C, and this is the compensating currents. What are the after giving the PWM pulses to the voltage source inverter, the inverter has been developed these three currents per harmonic elimination in the system. So in the second condition, dynamic load condition, we have taken this result. The study the up to this point, load is constant. At this point, we have added an additional load to checking this performance. So in this performance also, the current we got less than 5% THD content, and these are the internal characteristics of the controller. And if you see the comparative analysis, so previously, previous work one we have verified several times, but here we have increased the what is the feature? If you see the features here, type of filter, oscillation, complexity, amplitude tracking, frequency. Previous some frequency is not that control is not applicable for that particular frequency tracking features. But in this control, this controller can work the frequency tracking ability, DC offset, accuracy. What is the accuracy we got? THD currents of the grid currents, grid voltages, voltage current harmonic eliminations capability, steady state dynamic harmonic elimination ability, grid synchronization, and sampling time. So these features we have considered for this one. So we have compared with recently published work. With my proposed control scheme. See, if you see all these features, my proposed control give the best performance. If you see the type of filter, it is adaptive. These also all adaptive filters. We have not compared the conventional because already we have compared with the previous work. So we need to compare with the previous, because they are not applicable for DC offset. They are not applicable for current and voltage harmonic elimination. They are not applicable for dynamic performance. So that is the reason we have not compared that conventional control scheme. So we have considered the latest published work. Then that control should be an adaptive. So we have compared the only adaptive control scheme, and all the features, type of filter, which is the type of filter, if you see the oscillations, if it is the complexity wise, if you see the frequency tracking, amplitude tracking, mainly thing is DC offset. Mainly thing DC offset. See, these control schemes are not applicable for DC offset. So only SOGA, the conventional SOGA also is not acceptable because it is failed actually DC offset rejection, conventional one. So after adding a DSO, double SOGA, SO is a second order, third order, improved second order. After improving the conventional control scheme, then only that controls are applicable for DC offset. So DSOGA is given the medium performance for the DC offset, and SOGA medium, and MCCF is not acceptable for MCCF, and MCCF SOCF is not acceptable, and MSOGA its performance is good, and the proposed combined of this combined control scheme is completely gives the better performance compared to the other things. And also one more thing, THD of the grid current and voltage. So if you're using this type of controllers, we can eliminate all the currents and voltages by using only a shunt compensator. So no need to install, no need to design a hybrid active power filter or a hybrid compensator. So by using only a single control scheme, by using a conventional, what is that? By using a shunt compensator, so we can remove current and voltage harmonics at a time. And the dynamic performance is very fine. Grid synchronization, and one more important parameter in the one drawback in the microgrid system is grid synchronization. So this type of controllers also can be applicable for grid synchronization. So the sampling time of my system is 50 microsecond. So in work three here, first in the first work one, only we have considered only for current harmonic eliminations in the microgrid system. In the second paper, in the second work, we have considered DC offset, current, and voltage harmonic elimination. These two things we have mainly considered in work two. So if you see the work three, what drawbacks we have found in the work two? What drawbacks? Because here for voltage harmonics eliminations, we have used separate controller. For DC bus voltage maintenance, we have used separate controller. For grid connected inverter control, we have used separate control. So we have used three controllers for this DC offset and dynamic performance and other things. So if you see this, we have used three types. That means what? So the complexity of the system is high. The complexity is little bit not more high, but the complex, if you are using more controllers, automatically the complexity is high. So here, that drawback we have considered the next one. So here we have designed a dual order, multiple fifth order generalized integrated control scheme. Only we have used one control scheme in this particular area to reduce the complexity of the system or complexity of the controller. But mainly thing in this work, we have considered only how to reduce the complexity of the control, how to reduce the computational burden of the microgrid system. That we have considered in this particular area, and this paper has been accepted in IEEE Journal of Emerging and Selected Topics in Power Electronics. And this is the complete internal structure of the proposed control scheme. See, you can see one is for voltage and currents, we have used the same control scheme. Here we have 4 stages. We have designed this control in different stages. In stage one, signal reconstruction stage. So in this particular reconstruction stage, this load current, 3-phase load current converted into 2 phases. After that, by using the MFOGA, we have extracted fundamental components from the load currents. After that, by using the inverse clock, the 3-phase currents we have given to the stage 2. Why in the stage 2 we have calculated the frequency? What is the system frequency? Because by using this load, maybe the frequency variation is there. So here, by using this type of controller, we can calculate the frequency also. So we have here the first stage is we have reconstruct stage, the signal reconstruct 3-phase to 2-phase. Then by using MFOGA, we have started fundamental components. After that, by using inverse, we have calculated the fundamental components. Then by using this fundamental components, we are given to the frequency estimation tool. By using this one, space phaser, real and imaginary part, tan inverse of this theta, we got the frequency of the system. So stage 3 is extract the fundamental component stage. Here also, by using these fundamental components, we have calculated net currents. The net current is already what is after adding this PV and this P switching losses of the inverter, we have adding these three parameters. We have these parameters. We got the net components. These net components and unit vector templates we are given to the PWM controller. These net currents and what is that? Grid voltage, voltages and currents also. All three parameters we have given to the PWM controller. So based on this, these currents, the PWM controller can generate three-phase PWM signals that directly we have given to the inverter. So this is the internal structure. The internal structure of the FOGA. This is the internal structure of the multiple fifth order generalized integration technique. So this is the results, simulation results and discussion, and we have here we have considered all the test cases. If you see voltage here, we have added voltage unbalanced condition. So we have added here steady state. So previous also we have SAG voltage harmonic elimination, voltage harmonic injection, because in the previous paper we have given for voltage harmonic eliminations we have given a separate control, that is multiple complex coefficient filter. But here we have used only single controller, and that control can be eliminated voltage harmonics or not. That we have verified in this area. So that is the reason we have given a harmonic voltage harmonic injection, and voltage sag also we have given, voltage swell, and then at this point we have removed the load and dynamic load. So all 1, 2, 3, 4 total eight conditions we have considered in this particular control scheme. So in the voltage unbalancing, see here the magnitude, all three magnitudes are different. All three magnitudes are different. So at the time how the current is, how the system is behaving. So steady state condition, how the system is behaving, voltage sag, voltage cell, and this is the, these are the load currents in the entire operation, estimated currents, error currents, error 1 and error 2 currents, though estimated voltage estimated. So after we are firstly we have given the unbalancing. So after that, after control output, if you see the magnitude is almost, the magnitudes are balancing. Almost the magnitudes are balanced, we see here. So in the steady state also the performance is fine. So this is the net current, proposed controller output of the proposed controller, and this is the quadrature component currents. This is the reference current, and this is the frequency of the system. Frequency also we have verified. So if you see the THD analysis of all the test conditions I have given here. So every test case we got less than 5%. Every test case we got less than 5%. This is all 8 conditions. This is voltage. This is voltage THD, and left side current THD. And if you see all the test conditions, the THD is less than 2%. I think it's less than 2%. This is less than 3%. The currents I got less than 3%. The voltage I got less than 2%. And these are the some real-time analysis by using the FPGA based system. So you can see voltage and current. See the phase difference of the voltage and currents is, see the voltage and currents are in same phase. That means what? If your voltage and current are in same phase, then the power factor is equal to 1. That means the unity power factor. That means we have sent the maximum power from the microgrid system to the utility grid with unity power factor. Here also you can see this is source current and error current, and this is load current and load voltage. This is steady state current without compensation. The current contains so many harmonics. After applying the controller, the current having less harmonics. And this one is dynamic conditions. So the first channel 1 source current. So here we have removed a load. We have removed a phase A load. So when the load is removed, see what are the variation in the currents and error currents. See here. So this is the current in the entire operation. The current is maintaining good THD content. And here also if you see, we have verified voltage, sag and swell. Only here I have given only two conditions, the four conditions. If you see, if you go through my paper, you will get all the information, and you can find all the result for the particular control scheme. So voltage sag and voltage cell also we have given. So if you see the result, so this is the real-time THD content, THD values we have taken. The first case, we have given only 5 cases. 5 cases, see here, voltage and current THD, see here, 3.2, 4.2, 3.2%. Just here, another condition 3.2, another condition 4.2. So that means within 5%. Based on the IEEE standards, the current we have to maintain within 5%. So every conditions we got less than 5%. So next thing is very important thing. We have to firstly we have to compare. We have to compare how our control is better compared to the other thing, other control scheme. That is very important thing. Otherwise otherwise we can't say that our control is the better good performance. So here also we have given several characteristics like filter category, complexity, DC offset. So several types of characteristics we have considered in this one. So if you see the proposed, these are the proposed system performance. These are the conventional control scheme. Conventional means recently published work. Recently SOGA, DSR, recent. These are the recent up to 2021 paper only we have considered, and we have verified all control schemes with our proposed control scheme, and the performance is all characteristics. Our control scheme has been given a good performance. And the work 4 in the next paper, what we have considered. And if you are using the fifth order, in the fifth order, if you see the work 1 only, we are not considering any other things. Only we are considered only for current harmonic eliminations in the system. We have to consider current harmonics in the system. So in the second paper, we have considered DC offset, and we have to consider just a minute. Okay, fine. So in the first paper, only we have considered only current harmonic eliminations. In the second paper and second work, we have considered DC offset rejection and grid voltage and current harmonic eliminations. So these two parameters we have considered in the second paper. And what drawbacks we have found in these two works. In the third paper, by to reduce or to minimize these drawbacks, we have developed another one to reducing the complexity, to rejecting the DC offset, and to reducing the mainly computational burden. So we have implemented another control for the one second. Yeah. So we have designed another control for computational complexity. But in that also, because if you are increasing the order of the controller, because in the previous work we have designed a multi-layer fifth order based controller we have designed in the previous one, but the performance is very fine. But if you increasing the order of the controller, the complexity of the controller is little bit high. So that thing also we have considered in this particular work. So in the work 4, we have designed a controller. That controller is it should be adaptive. That this controller should be adaptive, and this controller should be very less complexity compared to the previous one. Only one thing we have considered. Remaining all parameters are same. DC offset, DC offset is same, and current and voltage harmonics is same. And here only we have considered instituting a fifth order harmonic. If you are increasing fifth order, automatic complexity of the system is high. So if you are using a reduced order, so if you are decreasing the order, and if you're decreasing order, and that if you're decreasing order also, then also the controller can work the DC offset, current and voltage harmonic elimination, and other adaptive parameter. That what is that? Amplitude tracking, power factor, frequency tracking. So everything should be should be covered in this particular work. So that is the reason in this paper we have developed a reduced order based controller we have developed in this particular work, and this paper has been accepted and published in IEEE transactions on industrial electronics. So here we have taken a conventional reduced order control scheme, but here we have improved the control scheme. We have improved the control scheme by this cross coupling. So after this cross coupling, what modification we have done? Conventional ROGI we have taken, but we have simulated this conventional ROGI. So after that we got some characteristics of the system. But after modifying this control scheme, we got a better performance or better, more accurate. We got the more accuracy from the conventional compared to the conventional ROGA. So that is the reason. So we have modified the conventional ROGA. Then we got the alpha beta, that is quadratural in phase components of the currents, and also we have calculated the frequency by using the FLL. And these are the complete control structure of the proposed control scheme. Here we can see load currents we have given ABC to alpha beta, then modified control scheme we have applied, then we have calculated alpha beta component. Alpha beta component is nothing but in phase component. First alpha is the quadrature component and this is beta is the in phase component. By using inverse Clark, we have converted two phase into three phase. That after that sampling a whole circuit and zero cross intersection, by using this thing we have found the absolute value of the these three currents, ILA, IA, IP, RCIC, and also one more important parameter is what? VDC, losses of the inverter also we have included, and one more important PV feed port components so we have included in this particular area. Then we have calculated the net current. By using the net current and unit vector template voltage, we have calculated the three-phase reference current. Three-phase reference current and actual currents we have given to the PWM controller. So by using these two currents, reference current and actual currents, the controller can calculate the switches of the inverter. So S1 to S switch S6. So all switches, all PWM signals we have given to the grid connected inverter for the harmonic mitigation in the system. So this is the simulation result. Here also we have considered different test cases like grid dynamic and grid dynamic conditions. Also we have considered load, also considered, and all what are the conditions, what type of fault, what type of faults or what type of drawbacks are available in the microgrid system. So every conditions we have considered for this particular paper. So every test conditions we got a good result. If you see all the result from voltages and currents also, if you see the DC offset is 0, all magnitudes are maintaining a 0 offset, and all conditions, dynamic load conditions and dynamic currents, every condition that the controller gives the best performance compared to the other things, other parameters also. And also here we have given some internal characters of the controller. This is the alpha beta component of the current. This is the error current of the error current alpha beta component error. This is the final final I star alpha, that is fundamental components of the proposed control scheme. This is the net current, what we have calculated at the output, this net current and unit vector temperature voltage. So based on by using this current, these two parameters, the proposed controller is calculated three-phase PWM currents. And see quadrature components of voltages. Voltage also we have given because we have injected some voltage harmonics in the system. So how the control is responding during the voltage transient condition. So that also we have calculated. So this is the reference currents, last reference currents, and this is the controller calculated currents. And this is the DC VDC at we are maintaining this 375 volts. So at the entire operation, the voltage is maintaining 375 voltages. And see, these are the some few important experimental result. See the voltage and current, both VSI and ISA, both are in phase. Both are in phase means the power factor is unity. So in the previous what 3 also I have explained the same thing. If voltage and current are in same phase, then your power factor is 1, that is unity. Otherwise, your power factor will be lag or lead. So we have to maintain the power factor unity. Then only we can send the maximum power from the photovoltaic system or from the renewable energy sources to the local loads or to our grid, utility grid. And these are some what is that internal characteristics of the controller. And see here, this is the second case, voltage. What is the voltage swell condition? And this is, you can see voltage swell condition also. See the grid voltage, the DC voltage. See normal condition, the voltage is maintaining normal. The voltage is increased. The voltage, the what is that? The DC voltage is also increased. So that means what? Our proposed the fuzzy logic based PID control is working properly, and the combination of the fuzzy based PID and as well as this reduced logic controller. By using this controller, we can control DC bus voltage at a constant value and during load condition, and we can control the grid side converter, grid tied inverter with tied inverter with we can send by the applying this controller, we can send the maximum power with unity power factor. And this is the real-time THD analysis. You can see real-time THD analysis. So here in the experimental, by using the we have used an unconditioned bridge rectifier circuit. So we got with before compensation, we get 26.452%. So in the case 1, we got 2.261, case 2, 2.255, case 3, 2.289, and remaining case 4 to case 7, we got less than 3%. So all the 7 conditions, we have verified 7 test cases. So all the test cases, we got less than 5%, and that means what? It should be maintained less than 5%, because based on the IEEE 519 standard limits, we have to maintain the voltages or current THD is less than 5%. So all the conditions we have maintained the same THD. So here also the main important thing is comparative study. So we have verified, we have compared our proposed controls with recently published works. Each and every case, he said every characteristics, every behavior, every characteristic, we got good performance. We got good performance, and if you see the T accuracy also, accuracy is better accuracy, and the DC offset also we got almost zero. We got almost zero. It is better. It is giving the better performance on the DC offset. And current voltage harmonics also we have removed by using this single control strategy without using an hybrid active filter. And also error settling time is very less. The settling time of the controller is very less compared to the other second. See, the settling time is very important. So here remaining all 0.1 to 0.15 second and 0.1 second. Remaining controls are given more settling time, but my control is given 0.05 seconds. So which is very good settling, good accuracy, and good better settling time compared to the previous ones. So in this presentation, I have discussed so what is microgrid and what are the other things, what are the other drawbacks in the microgrid system, and what works we have developed particularly in this area, and what is the research gap in this particular area that I have discussed in this one, and what are the different types of controllers are available, and what type of controllers, what type of adaptive control schemes is developed here in this particular microgrid system that I explained here. And we have compared all these comparative study with recently published works, and also we have simulation works, and we have verified all the control scheme on simulation and experimental platform, and also we have taken all the result, and we have taken all THD contents under different test condition. And so what is the research gap? Particularly to see these particular power electronics based converters, power electronics based next few years, for this particular area is the huge research area. After 2 to 3 years or maximum 2 years, next coming 2 years, this particular area will be more trending research area. Now electric vehicle coming onto picture. So every electric vehicle, so you have to design the DC microgrid setup, or DC microgrid or DC based systems you have to develop for the electric vehicle based. And in the future system, everything will be power electronics. Everything will be, because if you see the statistics, now our India renewable energy statistics is 29% only. In the next 2040, it aims to 40%. More 40% or more than 40%. So now all microgrid systems, all systems is DC based system. The next next years, next 5 years, all microgrid systems are inverter based. What is that? Inverter based system. Everything will be power electronic based inverter system. So this system is very good research area in the next 5 years. Next 5 years to, I don't know, we don't know, but it is very good research area, particularly in microgrid system. And also what research gap. And firstly, mainly now the research is going on particularly in grid connected inverter control scheme or islanded based control scheme, islanded based control scheme. But in the future, the grid forming inverters. In the future, the grid forming inverters are the grid forming inverter is the best research area in the further years. Maybe only in India, only IIT Bombay is working, and me presently I am working on how to design a grid forming inverter. So what is the grid forming inverter is nothing but if suppose the grid is isolated, it is isolated from the grid. So in the future system is everything will be inverted based. So any one of the inverters or two inverters can form the grid, and it can give the power to the local supply. So without interrupting the power in the microgrid system. So that is the grid forming inverter. That is one of the excellent research area. Only in India, only one or two institutes are working on this area. In foreign also only one or two institutes are working on this particular area. So that is one of the research area. So next thing is, so you can develop any more less complexity, less computational border systems, controllers in this area. And also you can design more adaptive DC bus control for the electric vehicle. And another thing is reduced order control scheme. If you are using reduced order multi-level inverter based control scheme, also you can design in the future microgrid system. And also the next one, a buck boost based grid forming inverter we can design. So these are the different research gaps in this particular area and future direction. So these are some key journals or book chapter what I have published in the recent years, and these are by some references or citations what we have used for the what is the literature survey that I have given here. So thank you. So you can, if you have any questions, you can ask me.
Thank you, sir. Participants, if you are having any queries, you can directly interact with the resource person, or you can type the question in the chat box so that sir can answer that question. Sir, one question in the chat box. How
Okay.
controls are selected, sir? Why only adaptive control is most important?
No, how controls are selected. So based on your system, what type of loads you have used, based on that loads, how your system is behaving. So based on that, so if your system is stable, then you can use a normal control scheme. The normal control scheme, you can that controller can give the good performance, no problem. But steady state performance is not possible in our actual grid. In the simulation time, we can use only one steady state condition. But in the practical grid, the steady state performance is not possible at all. The grid is always changing their magnitude based on the loads, what we have connected to the load. Based on that, conventional things are not acceptable. The performance is not acceptable. And also, what type of controller you have to design? The controller should be less complexity, because that's the execution time you have to take care. And what type of adaptive? That means So you can use any adaptive control scheme that should be less complexity and that should be applicable for different characteristics like what is that DC offset. That is very important thing because we have to maintain the magnitude from positive to negative peak 0. Otherwise, what are the equipments what you are connected to the domestic applications, the laptops, TVs, some other applications, it will be damaged. So based on that, you have to select your controller and that controller should be applicable for all the applications, all the characteristics.
Still any more questions, participants? Sir, one question in chat box again.
Yes.
Generally, for any work, we use PID controllers, neural network controllers, FLC, adaptive or AI controllers. If we observe any published papers, they compare controllers. My question is, what is the main parameter of error?
What is the main parameter?
They have written like that only, sir. What is the main parameter? In brackets, they have mentioned error.
So, if you see, the question is not actually, I'm not understood question. What is the main parameters for designing the controller or something?
I will unmute them, sir, so that they can directly interact with you.
Yeah.
Subhash, sir, you are unmuted. You can directly contact with the sir.
Yeah, hello, sir.
Hello, sir.
I think, am I audible, sir?
Yeah.
Sir, you just now you told me regarding the microgrid farming inverters.
Yeah.
What should be the specifications of that microgrid farming inverters and how many consumers we can supply?
Consumers are unlimited. The end users are the same. Everything is a microgrid is same microgrid, but now microgrid is what only grid following inverters. No grid forming inverters is not available till now. Now this is the latest trending research area. So parameters what we have considered particularly in the grid forming inverters are voltage, frequency, phase angle, and power factor. These 4 parameters we have to consider for designing the grid forming inverter. So now the research is going on. So after publishing of some paper, then we can get an idea.
And one more thing, is it like a simple inverter which we are using in the home?
No. That is completely different inverter and different control strategy.
Okay.
That is completely different inverter. That what we have used now what we are using inverter, that is completely grid following inverter, not forming inverter. So grid forming means suppose grid is isolated from the microgrid. So any one of the inverter can form a grid, or it can give the power to the loads continuously.
Yes, sir. At our homes also, whenever the supplies goes up, then we are utilizing the inverter. In the similar way, we are applying for the grid also.
Yeah, that is the different thing. Yeah, that is okay. You are talking about normal inverter. Suppose if your grid is
Simple concept. I'm expecting to get it, sir. Just same application you are doing for the grid also.
Same type of things.
Okay.
Almost.
Yeah, but the thing is, specifications will be different from these home applications.
Yeah, the specifications are different from the normal microgrid inverter and this grid forming inverter.
What are the requirements to be form the grid forming inverter? What are the needs needed?
Requirement means voltage. We have to take care of the voltage, and the grid is grid is weak or strong. If the grid is weak, then we have to consider that thing. If a grid is strong, then grid forming is not a thing. So if the grid is weak or medium grid, then you have to consider that parameters.
And for the grid forming inverter we are getting the supply from the renewable energy source also. When main grid is disconnected.
Yes. Renewable energies.
Okay. Thank you.
Okay, sir.
Dr. Lakshmi, ma'am, you can now directly interact with the sir, ma'am.
Good evening, sir.
Yeah, good evening.
Sir, as you mentioned in the PPT, that different controllers are, as I asked you a question in the chat box, different controllers are used for based on the loads.
Based
Is
on
it
the
correct? So if we are considering based on the loads, the controllers, if we observe many papers, sir, they publish the papers by comparing two controllers for one application.
yeah.
Like if you take example of in smart grid or any electric vehicle, if we take a transfer function or we do by mathematical modeling or by any simple systems, they directly use a PID controller. My question is, why we have to go for a controller? So as you answered earlier, the purpose of using a controller is based on the load to balance or to reduce any error in the system. So how to choose a controller? Suppose I may, for my application, maybe open loop is better or sometimes closed loop is better or P controller, PI controller, PD. So how do I choose? Is it a trial and error basis or what is the procedure?
So you can use trial and error method, but so if your system, suppose if you're choosing a PID controller, then if you are running a system, then suddenly your system is not stable. Maybe some, if you're adding a load or something based on, suppose if you're adding an electric vehicle you added for the DC bus, right? So if you're using a PID, then not only electric vehicle, some other DC loads also connected at the DC bus terminals. So if you're using a PID, if you're running the system, then suddenly the voltage may be increased or decreased. So the PID control performance is not acceptable at that time. So how you are using the PID? So you have to choose another control. So which should be work under the voltage variation. Maybe the voltage will be vary. So if you are using electric vehicle, the voltage should be constant. So that is the reason. So you have to consider any suitable control scheme. So you can choose the trial and error method also. You can choose. First you can choose PI if it is working properly or not. I'm 100% sure if you are using PI, dynamic condition it won't work. PI, PID, these conventional control scheme. So you have to choose any fuzzy logic, any artificial neutral, any any other control schemes. So based on that, first, what is the behavior of our grid? What is the behavior of our system that we have to analyze first? So based on our system, we have to choose our controller.
Thank you, sir.
Thank you, sir.
Thank you.
Surely you have enhanced the knowledge of the participants in the areas of the microgrid adaptive control techniques, sir. Your discussion from introduction to microgrid to research areas that are applied in the microgrid and future scope for research areas is very much informative, sir. Thank you very much for spending most valuable time in our session, sir.
Thank you very much, sir. Thank you.
One more question is there in the chat box.
Okay, sir.
If we use UPQC, we have 2 inverter. Which controller is best suited for UPQC?
So unified power quality, that means it is a hybrid based controller, UPQC. So you can design any type of controller that is based on your system, based on that thing. You can use conventional or you can use an adaptive. But conventional, as of my knowledge, as of my literacy survey, the conventional performance is not acceptable. So better to choose any reduced order control scheme for the UPQC, Unified Power Quality Condition. Any reduced order controllers for both the series and shunt, both.
Okay, sir. Thank you very much, sir. Thank you very much for spending most valuable time with us.
Thank you, sir. Thank you for giving the opportunity. Thank you, Dr. Sir. Parashuram sir. Parashuram sir, are you here?
Okay, Naren.
Sir. Thank you.
How are you?
Yeah, very fine.
Okay, your session was good.
Okay, sir. Thank you for your good feedback. But it is taking